Let's take a quick look at two other examples of constant potential systems. So we're going to look at a finite well. So in this case, it's kind of like a particle in a box, except rather than having the potential go to infinity at the edges of the box, we have the potential going to some constant value. So inside the well, it's zero potential, and at the edges of the well, we have a constant potential, not an infinite potential. And then the other one I want to look at is if we turn this upside down. So we have zero potential, and then we have this barrier that we have to climb over. So we have some constant potential barrier, and we have free zero potential particles on either side of that barrier. Let's start by looking at this square well. So let's use what we know from what we've looked at in terms of constant potential solutions to the Hamiltonian, and also thinking about our particle in a box will be helpful. So we know that out here in the regions that are outside our little well, in this region, that we could have energies that are less than V naught. So inside the well, we could have an energy level that is this much, and that would mean that outside the well, our energy would be less than V naught. So energy would be less than V naught. So in that case, we know that we have a wave function out here that is going to be real. So it's going to have some normalization coefficient, and it's going to be e to the kx, because in this case, x is less than 0 in this region, and so I need to use the e to the kx version of that wave function, so that my wave function will not be infinite. And then over on this side, we still also have e being less than v naught, and so my wave function is going to be real, and it's going to have some normalization constant, but in this case, we're going to have e to the minus kx, because in this case, x is greater than 0. And so we know what our wave functions look like outside of this well. So if this is my total energy, we expect this wave function to decay exponentially outside, and this one to decay exponentially like this outside. And then inside the box, we would expect to have wave functions that are very similar to the particle in a box wave function, because we have v equals 0, and we have energies that are greater than our potential energy. And so this first wave function, we would expect to look something like this. And if we have a second, an n equals 2 energy level, then we would expect this wave function to have a node in the middle of the box and a maximum out here and a minimum down here. And then it should go asymptotically to 0 outside of the well. So just using what we know from our looking at other constant potential systems, we can already start to draw and imagine what these wave functions would look like. So notice now that in this square well, I have a finite probability in my different wave functions. So this area underneath this curve, if I square my wave function and take the area underneath the curve, this area, so psi star psi dx, is going to give me the probability that the particle is outside the well. And I have a finite probability of being outside the well in those classically forbidden areas. So out here, when we have energies such as these bound state energies that are less than V naught, then these regions outside here should be classically forbidden. So as long as my energy, my total energy is less than V naught, I have these bound states that are quantized, right? So I have quantized energy levels. And they're bound because the particle is restricted to be in or near the well, right? It can't get too far outside the well. It can get a little bit outside the well, but it can't get too far outside the well. So it's restricted to be in this region on the x-axis. So those are bound states. But I could also give my particle enough kinetic energy so that it escapes the well. So it has energies up here, where all of the energies are greater than V naught and greater than V equals 0. So the energy is always greater than the potential energy. Then in that case, I would expect that if the total energy is up here, that in this region, I have a lower kinetic energy because kinetic energy is just the amount that's not potential. And here, I would have a larger kinetic energy. So remember that our kinetic energy operator is proportional to the second derivative of the wave function. And so it's the curvature. Remember that the second derivative gives you the curvature of the function. It's the curvature of that wave function that's related to the potential energy. And so the more curvy, the more squiggly the wave function is, the higher the kinetic energy. So that means that, just as with photons, that if you have smaller wavelengths, you have higher kinetic energies. And so if I have a total energy that's greater than V naught, I would expect that the energy, the wave function right above the well would have a fairly high kinetic energy, and then the wave function outside the well would have a lower kinetic energy and would have a longer wavelength. So I would expect that the wave functions for states that are unbound, that are not quantized, should look something like the blue line. Notice that up here, if I have particles in the classically allowed region, that there are no restrictions on the wave vector, and the wave vector can be anything. And is not quantized. So it's only when I have energies that are less than V naught that those energies are going to be quantized, because in that case, when my energy is less than V naught, I'm confining my particle to be in this region in space. And when I confine the particle, that's when I get quantized energies. So now let's make some inferences about what the barrier potential, what the wave functions would look like for a barrier potential. So if I have a particle that is moving towards the barrier, so moving in the plus x direction, so the wave function for this particle, because I have v equals 0 out here, is equal to c1 e to the moving in the plus x direction, I k x. If that particle reaches the barrier, then it has the probability of being reflected from that barrier and going back and traveling in the minus x direction. So I have to include the possibility that my particles are also traveling in the minus x direction. However, when it hits this barrier, if the energy is less than the V naught, there is a probability that my particle is going to be inside that barrier. So inside the barrier, because the energy is less than V naught, I have a wave function that is e to the minus kx, and I have to use the minus kx because I know that my x's are greater than 0, and if I used e to the plus kx, that wave function would go to infinity in this region, and I can't have that. That's not an acceptable wave function. And so inside the barrier, I still have a probability that my particle exists. So if that probability is such that there is still a probability on the other side of the barrier, then I have to match my wave functions at the barrier, which means that there has to be a probability that my particle ends up over on the other side of the barrier. And if it ends up in the other side of the barrier, now the v is equal to 0, and so I'm back to my imaginary wave function. But at this point, I only need to include the positive going direction, particles moving in the positive x direction, because there's nothing out here that would turn the particle around and have it go back the other way. So my full wave function has 3 different regions. In the left-handmost region, I have particles going in the positive x and reflected back in the negative x direction. In the barrier, I have a decaying exponential, so I have some probability of being within the barrier. And if that probability does not decay to 0, then I have a probability of having my particles on the other side of the barrier. And this function needs to be continuous, so this is going to look like this. And then out here, I'm going to have also a sort of sine wave looking wave function on the other side. I would expect that the amplitude of my wave function over here, my C4, is going to be less than C1 and C2, because I would expect that the probability that I'm at this other side of the barrier, that I make it all the way through the barrier, is going to be much smaller than the probability for the particle being on the left-hand side of the barrier and being reflected, just being reflected and going in the forward and the reverse direction. So notice again, we have, so we would square this wave function, we'd find the area under the curve, and that would give us the probability that the particle is in a given region in space. And so there is this finite probability that my particle is inside the barrier and that it leaks all the way out and ends up on the other side of the barrier. So this phenomenon where I can have a particle start on one side of the barrier and show up on the other side of the barrier is called tunneling. And it is the basis of the scanning tunneling microscope that allows us to actually visualize and look at single atoms on a surface or in an appropriate solid. So we also could have the possibility where we have total energies that are greater than the barrier height. And so if my total energy is greater than the barrier height, then I'm going to expect that my kinetic energy over the barrier is going to be small. So I'm going to have a long wavelength when I'm over the barrier, but my kinetic energy on either side of the barrier is going to be higher, and so I'm going to expect a shorter wavelength when I'm on either side of the barrier. So remember that the curvature, how wavy that wave function is, tells me about the kinetic energy. So the shorter the wavelength, the higher the kinetic energy.